So the talk that we have here for you now is called "It Must Be Nice to Have Washington on Your Side," and so I'll turn the remainder of the time over to the team from Johns Hopkins University in APL. So here we go.
Oh, right on. I'll say my silly thing then while they're getting ready. I've spoken at ShmooCon before, but my team has not. These are all first timers, which is really awesome. Um, if so, to give them a proper ShmooCon welcome, you guys know in your swag bag you have one of these guys, and if you saw Bruce's talk earlier, you know what it's for, but you may want to get it out and have it ready just so, at the right time we can explain to these folks what speaking at ShmooCon is all about. I guess we're gonna do a little song and dance. I can say, I wasn't gonna sing the "It must be nice, it must be nice to have Washington on your side." Oh, you want it back? Yeah. Yeah. Okay, getting the thumbs up there. So, yeah, so we're going to be talking. Our talk is called "It Must Be Nice to Have Washington on your Side: Unlinking Binaries on the DARPA Assured Micropatching Program." I'm going to take my mask off. Our team is listed here. Me, Ozzy. We have Josh, Robert, Amanda, Jonah, and our pronouns are listed there. Just real quick on this slide, this work was funded by DARPA. We're a contractor to DARPA, so we don't speak for DARPA, but we'll be talking about kind of the program and what we did under it. So just some background information, kind of the motivation that really Sergey Bradis, who is the PM that ran this program. Oh, I am very sorry. I should say on this slide before we get started, we also have in the audience Jen Spiro, who did a whole bunch of work on our on the project. Thank you, Jen. And we also made a lot of use of Paolo Gentry, was a intern who's not here today, but we are also indebted to them for the work on the project. So thank you, Jen, and thank you, Paolo. The motivation for this is kind of some questions around why, we've made a lot of progress in computer security in kind of the enterprise space and even smartphones and things like that. If you think about what things were like, 15 years ago to now in terms of, just antivirus patching, things like that. Whereas those gains really haven't materialized in the embedded device world. The embedded device world is still kind of like the Wild West of security. We still have a big gap between the traditional software development world and the reverse engineering world. So we kind of live in the reverse engineering world. In the reverse engineering world, you usually spend a lot of time in your disassembly tools in Ghidra, Binary Ninja, IDA Pro, and you kind of make your databases, and maybe you use some of that information to patch some software or something like that, but you're not really able to feed that back to the software development community. And so these things were in Sergey's mind when he kind of kicked off this program. How do we bridge that gap between the RE and embedded development worlds in order to make some progress in security? So I'm going to be talking about AMP and what it is, the larger DARPA program. We're just a small part of that. Going to be talking about what we did on this project previously, code cut. Robert's going to talk about deep cut, which is a new machine learning approach to the code cut problem. Amanda's going to give a talk about code cut and give a demo. Josh is going to talk about unlinking binaries, and Jonah's going to talk about recompilable C. This is just a little bit about who we are. I'm not going to read this all off, but basically we represent kind of a broad spectrum of groups at APL. So one of the great things about APL is that we kind of bring groups from like a wide variety of expertise to solve these challenges. So we have kind of folks that work in RE, vulnerability analysis. We definitely work in embedded development and binary patching, and then we're also bringing in, Robert especially represents kind of the machine learning expertise. So we're able to pull these things together to solve problems, which is really cool. On AMP, so AMP is a large program. There are 8 different teams and then 1 team that does testing and verification. So I mentioned Dr. Sergey Bradis is the PM. We're part of the MineSite team, so we're actually a subcontractor to Siemens. And yeah, I mentioned there's 2 technical areas. Point of that is if you are kind of interested in this problem of embedded systems binary patching, but you're like, okay, I have that problem, but I don't really like your solution or what you're talking about. There's a whole lot of other stuff going on AMP. So you should definitely talk to us, and we can get you talking to Sergey to hear about all the other stuff that's going on. This is a picture of AMP and kind of what AMP is trying to solve in terms of embedded binary patching and how we fit in. So on the top, you see kind of your traditional build process for an embedded system. You have kind of a bunch of source files. You compile them into object files here. You link them, and then you get a single binary firmware blob. There's a satellite here because that's one of the kind of interesting. NASA is one of the government sponsors. They're very interested in this because they have satellites where they may have lost the source code, or they may still have the source code, but just the build tools are just so outdated that they don't really have a build chain anymore. They also want to be able to make as small a patch as possible. They don't want to have to like reload the entire firmware. They want to be able to like do a very small firmware diff. So the envision process in AMP, people are kind of tackling this a lot of different ways, but our team is looking at it as taking apart the firmware, so taking this fully linked binary and breaking it into object files, and then unlinking, which is kind of a new concept, and Josh is going to talk about his work there. So to recover object files out of a linked binary, decompile them, patch, recompile, and then push that patch. Where the split in AMP is some teams are working on the targeted decompilation problem, and then there's a whole other set of teams working on the patching problem. So we're not really working on the part of applying the patch and verify that it works, but there's a whole set of teams working on that. So we're mainly talking about code cut today and a little bit about unlinking here. So we've been working on this for a little while, and I actually spoke at ShmooCon2019 when and I had an initial breakthrough. We kind of spun our wheels in this problem for a while. the code cut problem, trying to recover the object file boundaries within a binary, is something that if you've been reversing for a while, you kind of know this intuitively. You probably kind of do it, without necessarily even thinking about it. But doing it in kind of an automated way has been like a difficult problem. We even had Robert work on it as an intern. He got some. I'm sorry. They had some. I guess you would say graph algorithms that were kind of working, and now that they're back as a full-time employee and got this team together, they put together a really awesome machine learning solution to the problem. So we're going to talk about that in a sec. We had an initial prototype for IDAPRO. It was like not great. Robert's also going to talk about the limitations of how not great it was. In the meantime, we developed a thing called All-Star, which is our data set for testing. And so in 2021, we joined the Siemens Mine Site team and got some funding to work on this. So I'll kick it over to Robert here.
All right.
Are we shifting?
Well, we're doing something. So thanks for the introduction, Ozzy. So the code cut problem that we're looking. Pardon? Better? Oh yes. All right. So the code cut problem that we're looking at is trying to take a compiled executable, mainly firmware, and trying to recover clusters of related functions. And so really we're trying to see, can we recover the original object files, the compiled units during the build process. So our approach to this is really informed by the original algorithm we had to this a few years ago, which relied on the insight that function calls are actually pretty correlated to this module division, to this division into object files, and it's really that if all of the functions in an object file are vaguely related, then they should have similar calling patterns. So they should either be calling similar or the same functions, or really that they should be calling other functions in the same module a lot more so than they're calling just functions from different modules. So you should really be able to split most of these function calls into either library calls or calls to other functions in the same module. So the original algorithm for code cut tried to use some signal processing heuristics to identify like a change in directionality. So the idea being that if most of the function calls are to other functions in the same module, then because object files are contiguous in memory, when you near the boundary, the beginning or end of an object file, there should be a change in directionality. If you're at a function near the end of the object file, most of the calls should be going upwards. But when you start the beginning of the next object file, most of the function calls should be then going downwards. And so there's some sort of signal processing problem here, and the original code cut algorithm used some signal processing heuristics to analyze these function calls and try and guess where these boundaries between object files are. And it sort of worked. It didn't work great. It's definitely picking up on a signal, but there was quite a bit. But it was quite a noisy problem, and it wasn't all that accurate. So our motivation going in is that we wanted to use more powerful tools to better extract the module divisions. So we really are trying to view this as the function calls, the function call graph is what's going to be informing our guess at the division of the executable into object files. And so the most powerful tool we can apply to that is graph-based machine learning. And then we also wanted to make use of some more principled graph theory algorithms as opposed to this signal processing heuristic. So the main tool that we're using is graph neural networks, and they are pretty much a direct analog of convolutional neural networks, which have achieved a truly incredible accuracy for machine learning on image-based data. And so the main convolution step of a convolutional neural network, it aggregates data from neighboring pixels at each step, and combines that with some nonlinear activation function and magical linear algebra. And when we want to adapt this to data defined on a graph on a network, then the natural step is that the convolution operation is aggregating data from neighboring nodes instead of neighboring pixels. Once you have this generalized convolution step, then you can just plug it in into your favorite machine learning framework. Here we used PyTorch Geometric, and really go to town. So one remaining difficulty of trying to use graph-based machine learning for this code cut module division problem is that usually graph neural networks are trying to predict properties of individual nodes, or maybe of the graph as a whole. But we're instead trying to do this clustering property. We're trying to find, we're trying to partition the graph. And there are some ways that you can try and force this into like into a node level prediction problem, but none of them are that good, or a particularly good fit for a problem. So we went back to the original code cut motivation, which is that the function calls, the edges connecting the nodes, should really be what's informing our prediction of these object file categories. So we trained the graph neural network to predict which function calls are between two functions in the same module versus two functions in different modules. And so you can convince yourself that this is really equivalent information to the module assignments to a proper object file partition. But it's substantially easier for the graph neural network to learn. And so this is because it's really a local prediction. You aren't asking the machine learning magic to predict something for all of the functions. It's really just predicting a two-option classification of each individual node. And so you can't have machine learning without an ungodly amount of data. And so to do this, we made use of the All-Star dataset, assembled labeled library for static analysis research, which is a fancy way of saying we took every Debian package ever, and took all of the compile and build information for each package. And so if we after filtering through this, we are looking at since our end goal is looking at trying to reconstruct the object file boundaries. We're only interested in packages which actually have a decent number of different object files in them. But we end up with around 80,000 80,000 different executables. And so we can extract the function call graph from each of these packages, and for training we could annotate it with some simple metadata about each function. And of course we only want to actually make use of features which would still be present in strict executables. And so we're only using information like how big is your function in bytes? For each function call, what's the distance in address space between the source and target? But now that we have a machine learning model and a massive amount of data, we can plug it in and press play. But we do have one remaining issue. That does sound much better. We do have one remaining issue, that the graphical neural network is not directly predicting any object file boundaries. It's trying to classify every single function call with the confidence that this function call, the source and target, are in the same module, the same object file. And so there's a big problem here, and that's that since we're just relying on machine learning magic, there's no guarantee that the output is consistent. As an example of what could go wrong, the machine learning output could say that function pairs A and B, as well as B and C, are in the same module, but that A and C are in different modules. And there's just no way to fully reconcile this. So we need to give our best attempt at reconciling all of these predictions to try and get discrete clusters of functions, to try and get a discrete set of object files. And so the tool that we use is taken from computational social science, specifically working at the graph's modularity. And so computational social science has quite a lot of problems which look at, I have an actual real-life social network, and I'm trying to figure out what are the actual friend groups and the like. And so one tool that's been applied is modularity, which is measuring the fraction of connections which are within a single module versus which are between modules. And so then we wanted to take the input function call graph, weight it according to the output of machine learning, and then try and figure out what is the partition which gives the optimal possible weighted modularity score. And so that's just going to hopefully correspond to the original object file boundaries. So we also get a bit lucky in this problem, in that we have a bit of extra structure that's not usually available in graphs, and it's that all of the object files are contiguous in memory, unless you're doing something very weird. And so this is then a bit of a easier problem than finding community structure in general, and we can make use of these two different types of structure. That there's the contiguous in memory structure, and then there's this function call graph structure. So we can combine those to efficiently determine the optimal partition. And when we glue all this together, we find that it works pretty well. The machine learning component gets a 97% accuracy. Ooh, that's not good. It gets a 97% accuracy at classifying the function calls as between two modules versus within one module. And so this doesn't translate directly to a 97% accuracy on the entire code cut problem. In fact, we find our accuracy drops a little bit to a 93% accuracy at predicting these object file boundaries, but it gets most of the job done. So there's maybe some maybe some more room for improvement in specifically the reconciliation algorithm. But this is a pretty good solution to the problem, and it achieves around a seven-fold improvement over the original approach to code cut, which was again based on signal processing heuristics. And with that, turn it over to Amanda.
So that was our. That was the theory portion of the of the talk here. So now we're going to get practical, talk about how we implemented it in Ghidra, which you can you'll be able to download here after the talk. And so Amanda's going to talk about that.
Okay, so I'm going to talk about the code cut and deep cut plugins that we developed for Ghidra. So again, the code cut goal is decompilation for a single object file by identifying object file boundaries in a linked binary. And the goal of the GUI is to allow users to really take those deep cut. Is that better? Okay. Take those deep cut results and make any manual changes to really interact with that binary at that object file level. So the first thing we did was develop the deep cut plugin, which is a Ghidra one-shot analyzer that runs deep cut against the current program that you have open. And the result is that every function gets assigned a module name in its namespace field. So it's implemented in Java, it's a Java analyzer, and it generates a function call graph that calls Python to run the deep cut machine learning model that Robert just spoke about. And then that model can also be used by other tools to generate JSON formatted function call graphs as well if need be. So once you run deep cut, the next step is to use the code cut GUI plugin, and I'm just going to go over some of the core functionality that we've implemented. So the code cut GUI plugin is meant for reverse engineers to really be able to visualize and work with the deep cut result, and again make any of those modifications at that object file level. So that's doing things like namespace modifications as in renaming, resizing, combining, or splitting. It's also modeled after the built-in Ghidra symbol table. So if you all are familiar, it has a lot of the same functionality. So symbol filtering, you could use regex or text, renaming or deleting functions, and then we can also drag and drop between the different namespaces. So in the case that deep cut may have assigned an incorrect module name, you could just drag that function into a different part of the table, and it will update the table as well as the namespace field of that function accordingly. We've also implemented some module name guessing functionality. So this is using Python and natural language processing to analyze all the different strings in the functions of a module, and it will come up with a best guess name for that module. This is really dependent upon the strings that are available in the binary, so it does have the potential to do things like picking up source file names, but that's not always the case. And then we also have a number of export options, so the users can actually use that code cut data. The first one is exporting a module map, so that is all the addresses of the object file boundaries as well as the names that the module name guessing stuff has picked up. And that could be useful in the case if you're working in a team or something and you have the binary at a good spot. You could export the module map, someone else could import it, and it will update their code cut table accordingly. You can also export as C, so that will take either an address range or a single function, and it will output those functions or that function as recompilable C source code, which Jonah will get into in a little bit. You also have the option to output an entire module, so that is all the recompilable C source code for all the functions in that module, as well as its relinkable elf or .o file, which Josh will speak about. And then lastly, we've also implemented a way of improving the Ghidra source to assembly mapping, which is used by things like the highlight functionality. So if you highlight some source code, it will highlight corresponding assembly language instructions, and a lot of times that's just like a single instruction or a couple. So we've actually improved that mapping to attribute more of those assembly instructions back to their respective C source code, and we're outputting that as dwarf information that comes with the ELF file, and it will map between that relinkable ELF file, its assembly instructions, to the line numbers of the recompilable source code to aid with any type of patching. And then we have a demo that... Okay, yeah, so this is just to show what CodeCut looks like and how you use it. Is that?
Did it?
Yeah, it's fine.
It's going. Okay.
Okay, so you open it like any other Ghidra plugin using the Windows tab, and once it opens, the first thing I'm going to do is set the Python executable path. The module name guessing stuff does require Python 3, so I'm just setting that in the tool options. And then the next thing I'll do is kick off the module name guessing. So again, this is going through all the different strings and the functions and coming up with the best guess name. In this case, I believe the binary had a lot of debug strings, so it's actually able to pick up all those source file names. And once it finishes running, it's going to update that left column of the table. I'm not sure how well everyone can see this, but that top one says object 1, and once it finishes running, it's going to update to cbc.c. And then I'm going to demonstrate the other functionality, so dragging and dropping. Say you've done some REing and transport handler doesn't look like a CBC function. You could drag that into a different namespace. You can also do things like splitting. I'm going to combine them into one larger namespace, or renaming. If the module name guessing stuff doesn't pick up anything useful, you could also, based on your own work, come up with your best guess and rename it in the table. And this step is really important for doing things like outputting relinkable.o files. So yeah, definitely take full advantage of all the different things that you could do to get those boundaries as close to correct as possible. Yeah, so this is just me renaming. And then the last thing I'm going to do is, once I think I have this in a good spot, I'm going to export the module map. And then once that exports, I'm going to open it to show what's inside of it. So again, that's the addresses of those object file boundaries. So it will append a .map file, and that is what CodeCut will take if you import it as well. And then in there, there will be the first column of addresses you see will be the module base. Then the next column is the module size, and the last is the names that are picked up by the module name guessing stuff. And now I'll pass it to Josh.
So that was a real quick overview. Thanks, Amanda. And there's obviously a lot of, if you're just reversing, so Josh is going to talk about unlinking. If you're reversing, there's actually a lot of benefits that gives you to be able to kind of work at the object file level, but we're not going to go into that a whole lot. We're going to kind of talk now about, Josh is going to talk about unlinking here.
All right. Yeah, so my name is Josh, and I'll talk about the unlinking of the binaries. And so first, I'll just say, so why do we need to unlink binaries in the first place? And Ozzy kind of alluded to it earlier, right? So there hasn't been a lot of gains in the embedded space, and so the ability to unlink libraries gives us a better way to maintain code for embedded devices. And there are two different scenarios, which I think Ozzy kind of alluded to earlier as well. Right, so let's just say APL developed something, but we lost the source code for the device, or we lost the build environment. Making changes to that firmware device becomes a lot more difficult now. Similarly, say if we bought a firmware device from a vendor, and that vendor either stopped supporting the device or they just went under for some reason. If we want to reuse any libraries from that firmware, it's a lot more difficult to do so. Additionally, if we want to patch or modify the existing firmware, it just becomes it's just a lot more difficult, or sometimes even impossible. And so then we kind of think about moving towards maintenance chains instead of your standard build chains. And then, so Ozzy had the image earlier, right, where you write your source code, you compile, and you get all your object files, and then you have your executable that you then ship out to your customers. But the ELF format is meant to be transformable in that you should be able to go from one view to the next. And I'll talk about views in the next slide, but the idea is that you should be able to go from this thing that you shipped out to something that's a little bit more manageable to maintain and modify. And so then we can start asking questions to what information should we save from the compiler, from the linker, so that transforming these binaries can be a little bit more tangible and maintaining them is a little bit more easier. And so here's just a brief overview of the ELF file format, and I won't bore you with all the details about the ELF file format. There's a lot of information on the web, but the main thing I want to talk about is the different views, as I mentioned earlier. So right, there's the linking view, which is when you're how to build executors, right? You have all your .o files that you then compile and link together to create your execution view, which then you would that's how when it gets loaded into memory, the CPU executes instructions, et cetera, et cetera. And so the linking view can contain something called relocations, and if you don't know what that is, it's like when you're writing your code and you call printf. The printf function is an external library call. When you compile it to a .o file that's relinkable, that it doesn't know where that printf function actually lives. So when it has a relocation to say, at some point, tell me where this printf function lives so I can then execute that function. And that's what the loader does when you actually load it into memory. And you can see in the image on the right there that the code and data blocks are very similar, and that's kind of where I mentioned that the L format is meant to be transformable. These two, the data blocks are kind of parallel to one another, right? So like when you're executing the code, they're called them segments, but when it's actually in a file, they're called them sections. And it's this transformability to kind of make this work somewhat possible, that we can go from this big executable to then try to unlink it to a smaller library that we can then relink with other libraries that we've unlinked with our code or with actual valid GCC compiled libraries. And so here's the general approach of our code here. So we want to use Giger's API as much as possible because code was built using Giger, and so we thought to have more continuity, we thought to use Giger's API. So the idea is to take a fully linked binary and unlink a single library from that, and the unlinked library should be transparent, right? So like if you use readelf or object dump or you want to compile it, it shouldn't be any difference between a library that I unlinked or a library that GCC then compiled. It should all just work together just fine. And so we wanted to use the output from CodeCut, obviously. So like the script would take in the library boundary. So let's say library starts from this address and ends at this address. And my script would take that and then gather all the relevant symbols and data and try to create a valid L file. And Amanda mentioned that it is important to get those boundaries correct and all the functions correct, because my script doesn't attempt to make any corrections to it. So if you miss a function that should have been in that library, if you try to link it, if another library depends on that function, it's not going to be able to find it. So you need to ensure that all the actual functions are contained within the library, and that's the beauty of CodeCut. You can actually go and change things around as you see fit. And so here's just a general high-level algorithm of the actual unlinking of the library. So the first thing I try to do is, if it is an actual full-linked executable, I try to parse the L file to see are there any sections and data that I can just sort of take as a starting point to sort of get myself kicked off here. And so I just check for are there any is the ELF header, can I look at the different number of sections, the different types in there, and I use that just to sort of get a bucket of different things that I can then go and modify and change later on. If that information is available, then I just sort of build everything from scratch. Then there's the gathering of all the symbols, and again, this is all dependent upon the libraries being, the boundaries being defined very clearly. And the script will go through and find all the different bytes, and it'll try to symbol relocation data as well. So if it uses Giger's cross-reference APIs to determine if a library is actually, or a function call is within a library module or if it's external. So I determine that to say if I have the library boundaries and I say, okay, it called function X. If function X is not within the boundaries, I determine that as an external library call. And then I say, oh, okay, well, zero out the bytes there, and then there will be a relocation at that address. If it's within the boundary, I'll just say, okay, cool, I don't have to do any more work. And then I go and modify the section headers, right? Because obviously, if I'm taking a big library and a big binary and bringing it down, the size of the .text section is going to change, the size of the actual offset of the sections are going to change as well. And so I have to make sure that all that is correct, because if it's not, then ELF is going to, or like GCC or readelf is going to say, hey, this does not look right, something's wrong. And I ran into that error quite a few times, and I had to actually go and debug actually like the readelf program. And so then after I get all the data, I'll have all the things that I need. I just write all the data to a file and kind of a sequential format to where it makes sense. And the thing that's really nice is that it doesn't really matter the order in which you write things. As long as the ELF header is up top and you tell it where everything is supposed to be, it's going to be just fine. But let one byte not be in that right place and everything goes to crap. So that was kind of irritating, but I was able to work through some of those issues. And the input and output to the script is very simple. So on the left-hand side is what the script does. It just pops up a list and says, hey, what module do you want to export? And this list is taken from the namespaces that CodeCut generates, and the user, they select a module. No other input is required from the user at this point. Just you better hope that you'll have all the functions in there, otherwise it's going to be not a great unlinked library. But assuming that you have everything correct, it will generate a valid ELF file, And as you can see from the right-hand side here, I meant to highlight it, but let's see, hopefully you can see that this is a relocatable file, and this was taken from a larger binary that we had in our possession. And so that's about all I have, and I'll give it over to Jonah.
Hello. This thing? This thing. Okay. So I'm going to talk about the recompilable C portion of CodeCut, which was implemented with the Ghidra Python API. So the idea of it is that the Ghidra ingests a binary and then outputs some decompilation. And if you take a look at it, it's actually pretty close to being recompilable with a few issues. It's designed to be readable, not recompilable, but with a few modifications, you can actually get it really close or there to being recompilable. So there's a few issues, and I'll talk about them now, and then I'll talk about the solutions to those issues, and then some work that's still left to be done. So the first issue right away is that there's external symbols, functions that are defined elsewhere. And you don't really know where they are just with a binary or the information that you're given. And then another weird Ghidra specific thing is these things called Ghidra intrinsics or internal decompiler functions. And what these look like are the concat function, which is concat31, which essentially just smooshes 2 bytes together and then outputs the concatenation of those inputs. And then the subtraction function, or subtraction, which is a truncation function on 2 inputs. And then there's the issue of undefined types. So if Ghidra doesn't know exactly what a data type is, it'll just say it's undefined. And it generally knows what the size of it is, but if it doesn't know what the exact type of it is, it'll just output undefined. And so if you try to put that binary, or put that C through something like GCC, it'll complain. And then lastly, there's a very strange memory syntax that Ghidra will output. It'll do something with offset and numbytes. And what this means is it'll try to access a property, generally in a struct, and it'll try to access it at offset, and then the length of it in numbytes. So there's an example here where it accesses the 4th byte in read frame copy, and it has length 2, and then assigns that to the 5th byte in CTS data. So these are things that if you were just to put this C code directly through a compiler, it wouldn't actually output anything for obvious reasons. And so some solutions to that are the external outputs. We can just find all of the external functions using the Ghidra Python API, and then prefix that with extern in a ghidra.h file. So we're basically saying let the linker handle that. And then we can define the Ghidra intrinsics, the concat and subfunction, as well in a ghidra.h file. We do the same thing with the undefined types. Since we kind of know what their sizes are already, we can just essentially put them in there. And then the weird memory syntax can be translated to something a lot more readable. So if we observe that there's any of these unaligned memory accesses, like here, we can translate it to something a lot more sensible. We know that since the size of the byte is 2, it's probably an unsigned short, and we know exactly where it's trying to access it because of the offset. So you can see that it's accessing the 4th element in reframe copy, it's casting it to an unsigned short, and then passing it to be or assigning it to be the 5th element in CTS.data. And then that's kind of how we handled the issues back here. And there's a few unhandled things. So firstly, we don't actually do anything with stack canary checking yet. So the _stack _check guard, we're not disabling that. And then there's another issue as well where if you've ever looked at decompiled C code with Ghidra, you'll often see this weird &stack OX offset thing. And generally what this means is that the decompiler is recognizing that there's a stack access, but it's not really, it doesn't really know where that's coming from. And so what this generally is that there's a mismatch between what Ghidra thinks that the input parameters to a function are and what's actually happening. And so this generally means that there's an error and the user has to fix the exact input parameters to the function. And so yeah, that was the recompilable C part. If you want to download CodeCut, it's here at this URL, github.com/jhuapl/CodeCut, and it supports Ghidra 10.1, 5, 10.2, and 10.2.2. I guess I'll give it to Ozzy.
That's all we have. Okay. Thank you all. Yeah, I was gonna say this is a good time if you want to get up and stretch and like get your arm moving. Thank you for sticking through it. A very technical talk on a Sunday morning at ShmooCon. I know Sunday morning's always rough because of the Saturday night parties, but we thank you for being here, and we'll take questions, I think, if we have a couple of minutes.
One, thanks for doing this, so none of us have to. It's pretty badass. And then my question is, what's next for you guys? Do you have any other projects related to this, or
So the comment was thanks for doing this. You're welcome. The other question was kind of what's next for our team. What are we working on? What we're working on with the rest of MindSight is we've also been working on extending the Ghidra decompiler with Python extensions so that you can do Python passes in the decompiler. Jonah really wanted to talk about that today, but we had to kind of keep it to one theme. But we're hoping to that's something we're also hoping to kind of open source. We're actually trying to we'd like to work with the Ghidra team to get that upstreamed, but that's something that it allows us to do a lot of like research within the decompiler. So that's the I guess that's kind of the main next thing that our team's working on. Question over here.
have you used any obfuscation techniques for like particular firmware blocks that your compiler has had trouble accepting?
Yeah, question is obfuscation techniques that CodeCut would have trouble on, and you're definitely right. We generally, when we're using CodeCut, we're usually working with just commercial firmware, right? So when you develop commercial firmware, you're not trying to be real tricky. You're trying to just make everything work, compile and that kind of thing. But you're pointing out a really good thing, which is that if you play any kind of compiler tricks, you can really mess things up. You can really mess disassemblers up, right? So if you don't, if your compiler doesn't follow the standard ABI, passes parameters in weird ways, you can really mess with the disassembly. So if you have some kind of like packed malware or something like that, CodeCut's really not the tool for that. It generally works pretty well on commercial firmware because, like I said, those are usually very well, organized. They behave well, let's say. Cool. Well, we'll hang out for a little while and love to talk reversing with you. Thanks, everybody.